You're watching a Channel 98 NBISD TV production.
Welcome to another edition of That Geometry Show. As always, I'm your host, Kevin Corpy. And whether you're tuning in for the very first time because you've been wanting to see what all the buzz was about, or you've been watching since the very first show, I would again like to welcome everybody, old and new. I've got a very special lesson I put together today. I'd like to call it Lesson 11. And it's all about the very, very popular geometric figure we've been using from the last couple of weeks, triangles. Now today we're going to be looking at some very special line segments associated with triangles. There's 4 special types. And we've got a lot of definitions and a lot of examples, so I really can't spend any more time sitting here greeting you and welcoming you to the show. But again, welcome. And let's get right to it. If you haven't already, first download those documents from www.newbraunfels.txed.net and we will get going. All right, today Lesson 11 is going to correspond with your Geometry Glencoe book, Chapter 5.1. This week we are again sticking with our topic from the last 3 weeks, triangles. They are a very popular geometric shape. There's a lot of information that goes along with them. But today we're going to be focusing on some new definitions of 4 special segments. So there's going to be a lot of memorization involved. You're going to have to get all 4 definitions straight before you attempt your homework that your teacher is going to be assigning you. And once you have those definitions memorized, then it's time to put them into practice. So I'm going to quickly go through the definitions, and then we're going to go ahead and work some examples. All right, the first special segment in a triangle that we're looking at is called the perpendicular bisector. And the perpendicular bisector is exactly what the name says it is. Perpendicular means 90-degree angle, if you remember. To bisect something means to cut it. Sect means to cut, two in half. So we're going to be cutting something in half using a perpendicular line. So here's the formal definition. It's a line or a line segment that passes through the midpoint of a side of a triangle that is also perpendicular to that side. Now, perpendicular bisectors do not always pass through the opposite vertex. So if I look at this triangle here, and I wanted to find the perpendicular bisector for this bottom side here, it would be a line that's perpendicular to it, and that's denoted by the little right angle box right here. And it's going to cut this segment down here into 2 equal parts, and again we denote the 2 equal parts by doing the tick marks down here. So this would be a perpendicular bisector. Okay? Notice that this line does not pass through the vertex of this triangle, but it is perpendicular and it cuts the opposite side into 2 congruent segments. And another definition, this one's called the median. The median is also a special segment that connects a vertex of a triangle to the midpoint of the opposite side. And every triangle has 3 medians, just like I didn't mention it, but every triangle has 3 perpendicular bisectors. Now this is very similar to the perpendicular bisector because it's going to bisect or cut the opposite side into 2 equal parts. The only thing that's different from this one is that this one starts or originates at the vertex of the triangle that's opposite the side. So if we look at this triangle here, I can start at any vertex. Let's start at the top here. If I come down to the side opposite and I eyeball or measure the point that's halfway between here and here, it might be this point here. So now if I draw a line from that vertex to this point, which is already drawn here, that should cut this opposite side into 2 equal parts. So we put the double tick mark here and the double tick mark here. Now notice that this is not a perpendicular bisector because this line right here is not perpendicular to the base. It's not at a right angle. And again, I could start, if I just rotate my paper, I could have started at this vertex, found the midpoint on the side opposite, which would be about right here, and then draw a line from the vertex to the opposite side, making 2 congruent segments with a single tick mark. And again, I could have started from another point right here, this vertex, drawn to the opposite side at the midpoint, making 2 congruent segments. So notice that the 3 medians from each of the vertices not only bisect the opposite side, but they also are concurrent, which means they all 3 intersect at a common point on the interior of the triangle. And that'll be coming up again later in the lesson. Okay, so that's a median. Median cuts it in half, starts at the vertex of the opposite side. Another definition, the altitude. The altitude is a segment that is perpendicular to a side of a triangle, much like the perpendicular bisector, and it intersects with the vertex on the opposite side, which was similar to the median. Now, most altitudes rise from the base, and their length can also be considered, this is important, the height of the triangle. But any side can have an altitude. So there's three different cases here for an acute, right, or an obtuse triangle. If I look at this acute triangle and I start at a vertex, which is what the altitude does, it's kind of like hanging a plumb bob, if you know what that is, straight down from the ceiling on a string and letting the weight just hang straight down and come to a rest due to gravity. This would hang from the vertex and come straight down and form a perpendicular angle with the base. Now this would be the altitude. We call it A, or we can also call that the height of the triangle. Now notice why this is not a perpendicular bisector, because this segment right here and this segment right here are not necessarily congruent. They don't have to be the same length. Okay? And that's why it's not a median as well, because a median would come from the vertex and cut it in half. So an altitude is always from the vertex straight down perpendicular to the other side, and it's the height. Now in a right triangle, if I look at this vertex here and drop it straight down, I actually get one of the legs of the right triangle. So in a right triangle, one of the legs could be considered the altitude. And in an obtuse triangle, if I look at this vertex up here, I'm going to have to drop a perpendicular line straight down on the exterior of the triangle. So this would be something that we call an exterior altitude. And that's what we get when we have obtuse triangles. Okay, so an altitude, the only requirement is that it comes from the vertex and forms a right angle on the opposite side. Doesn't necessarily bisect the side opposite. Okay, that's 3 of the 4. Now we're moving on to yet another important one. Last but not least, as they say, this is the angle bisector. Now the angle bisector does exactly what the name says. It bisects or cuts in half an angle. So a special segment of a triangle that bisects the angle of the triangle and intersects the opposite side. Okay? So let's look at this triangle. Let's take this angle up here that's formed at this vertex. If I divide this angle into 2 equal parts, this one and this one, the line that would do that would come across, and again, it would intersect the other side of the triangle. Since this cuts the angle into 2 equal angles, then we know that it is an angle bisector. But it might not be a median because these 2 segments, again right here, may not be congruent. They're not necessarily the same length. And it's also not necessarily perpendicular. So we can't call it a perpendicular bisector. We can't call it a median. But we do know, because these tick marks are here, that it is an angle bisector. So the notation, the marks, the tick marks that we draw when we're creating these things are very, very important. Now again, every triangle has 3 of all the special segments I've been mentioning, and this is no exception. So if I had chosen this, I could draw a line that cuts this into 2 equal angles, noted by the double tick marks here, and wherever it intersects the other side would be a point. But again, it may not be a right angle, and these 2 segments may not be equal. Now notice that if I drew all 3 angle bisectors, they would also intersect at a point of concurrency. That's what we would call it, a point of concurrency. Okay, which means that they all intersect at the same point. And that point will come up later in the program. There is a special name for that point. Okay, so we've looked at 4 special segments, and I hope you have them all straight, because now it's time to actually draw an example of each. So what we want to do now is draw a triangle RST, that has a median of line segment SN. So the first thing that I like to do is just draw a generic triangle. Okay? And I usually put a flat piece on the bottom, call it the base, and then I have the tendency to start labeling from the bottom left in the clockwise position. So I call that R, S, and T. It doesn't really matter how you draw your triangle or how you're labeling it, so long as you get a point and you're consistently going around. So now that I have it drawn, now the median has to be SN. So I need to get vertex S involved, and I need to create a point N. So remember what the median does. The median starts at the vertex, which will have to be S, and it bisects the side opposite. So if I look at this side down here, RT, instead of measuring, which your teacher might have you do, I can kind of eyeball where the middle would be. I'm just going to kind of put it right here. that would be point N. So that when I draw the line segment from point S to point N, what I have done is I've created the median, which means that this side is congruent to this side, or segment RN is congruent to segment NT. RN's measure is equal to NT's measure. Now again, if you're creating these things and you don't put those little tick marks, how is the teacher or the person looking at your paper going to know that you intended those to be equal? So those marks are very, very important. Okay, let's move on to another example. Triangle ABC with an altitude of BD. So again, we just create a generic triangle here, and I label it ABC, and we trying to draw the altitude, which has got to get point B involved, vertex B. So remember what the altitude was. That was kind of like hanging a plumb bob, letting gravity do the work. You're dropping a perpendicular line straight from the vertex B. So come straight down, boom, and we have to show it's a right angle by putting our little square box there. That would be an altitude. And I better go ahead and name that point right there, point D. So that segment BD is the altitude or the height of that triangle. Now again, without that little right angle box there, how is anyone supposed to know that you intend that to be a right angle? AD, the measure, and DC, the measure, may not be equal. Okay? An altitude just says drop it straight down. And then we want to draw one more here. We want to draw a triangle XYZ. So again, I can use the same triangle. Here's X, here's Y, here's Z. Now I want to draw an angle bisector called segment WZ. So I got to get Z involved. And it needs to be an angle bisector. So again, I can kind of eyeball a line that would cut this angle Z in half. And I'm just going to try and draw it in like this, and then I'll extend it to the other side. Now wherever it intersects, we're calling that point W. So this would be the segment WZ. And if I just walked away like that, how is your teacher supposed to know if you intended this segment WZ to be any of the four special segments? We need to put our angle tick marks. We can do one arc there and one arc there, and that will signify that those two are exactly the same measure or that they're congruent. Okay, got it? When you're doing your homework, you need to memorize what all four of those things are before you attempt your homework. And then as you're doing your homework, try not to look it up unless you absolutely need to. That way you are reinforcing the definitions in your head in the context of the homework. You will remember them much more easily. Okay. Now here's a couple of multiple choice answers here, and then we're getting ready to take a break. In which picture is segment AD the angle bisector? Okay, well let's look at choice A. We have triangle ABC, and we have a line drop down that is obviously a perpendicular. There's no other distinguishing marks, no other tick marks, so all we can say then is that segment AD in this case is an altitude. Okay, so that's not our angle bisector. If I come over here, I notice that I have a perpendicular line, but it's not an altitude because it doesn't pass through the vertex. But it does make these two segments congruent, so this is just our old perpendicular bisector. Perpendicular bisector. And that's not the angle bisector. That cuts the segments in half and not the opposite angle. Moving on over here, choice C. I have line AD, or segment AD, drawn from the vertex A that is bisecting the two sides. Notice the two tick marks. So all I know in this case is that segment AD is the median. Okay, median means middle. If you're ever driving down the highway, the grassy patch in between the roads is called the median. It's in the middle. So this comes right down the middle of segment CB, or cuts it in half. So by default, I guess this must be my answer. Let's see why. Notice the tick marks that are drawn in here. So segment AD makes angle CAD and angle DAB the same measure. So this must be an angle bisector. So the correct answer choice is D. All right, moving along here. In triangle ADC, segment AB is the what? Well, we'll look at all these tick marks here. Well, first of all, I know that AB is drawn from the vertex, and it bisects the opposite side. Notice the two tick marks. So I know that anything that's drawn from the vertex that bisects is a median. So yeah, it's the median. Now don't just circle A and move on, because notice on choice D it says all of these is a possibility. And if you just circled A, you would not be putting the best answer. Could it be an altitude? Well, it's dropped straight down from the vertex, creating a perpendicular. That's the definition of an altitude. So yes, it is an altitude. Now, because it's a median and it's an altitude, it has to be a perpendicular bisector because it combines both A and B. It's perpendicular, notice the little angle mark, and it cuts the segment in half. It just happens to be a perpendicular bisector that passes through the vertex. So yeah, that's true. The answer is D. This is actually our isosceles triangle. We have the two base angles congruent, so the sides opposite are congruent. Okay, triangles, triangles, triangles. We need a break from those triangles. Let's go ahead and take a break while we're soaking up some very valuable public service announcements, and we will be right back to work more examples about triangles.
Bad people, the gang members in the neighborhood. My brother, he wouldn't be happy at all if I was to tell him I was going to drop out of school. He would not approve of that, because then that's going to be two of us not handling our business.
Me and my friends are close and we all believe in each other. I know they could graduate, even if it takes them longer than the 4 years.
We have classes together, so
we study together, we help each other with our homework.
realized we messed up in the past.
Failed a couple classes before, not doing as much work as I should be doing. My two best friends, they keep me working hard.
Hey, welcome back. I hope you're still hungry for that triangle knowledge. Let's go ahead and hit that triangle buffet again. Okay, another example. We got triangle CPR, and it has vertices at these points right here, 15, 1, 9, 11, and 2, 1. Determine the coordinates of point A on segment CP so that segment RA is the median of triangle CPR. What does all that mean? That's a mouthful, okay? Well, what we need to do when we have a word problem is read carefully. Drawing a picture and labeling can help us really sort out the information. So here's a little grid right here. I'm going to go ahead and plot my points. Point C is at 15, 1. So here's 15, 1. I'll call that point C. I've got point P at 9, 11. So here's 9. I'll come up all the way to 11. There it is. And I'll call that point P. And then point R is the point 2, 1, which is down here. So now if I take my handy-dandy New Braunfels Independent School District ruler and connect the dots here, I create a nice little triangle. And once I have the triangle, I can try to make a little bit better sense of what it is being asked of me. Okay, so there's my triangle. I better call this R. Now determine the coordinates of point A on segment CP. Here's segment CP. See, we have something to look at now. So that RA, I need to draw a line from vertex R to the opposite side so that it's the median. Okay, well, I can eyeball it here, but since I'm on a coordinate plane and I actually have numbers, I can do better than that. I'm basically looking for the point that's halfway between P and point C. And we talked about a midpoint formula on a previous episode. If I have 2 points, x1, y1, and x2, y2, then the midpoint, if you remember, the coordinate of the midpoint is just going to be the averages of the x values. So x sub 1 plus x sub 2 divided by 2. That's your new x coordinate. And y sub 1 plus y sub 2 divided by 2. The average of the y values is your two new y coordinate, or your new y coordinates, sorry. So if I'm looking at point P and point C, that's these two up here, I can find the new point. So we'll say that point is going to be called point A. So point A will be 15 plus 9 divided by 2, comma, 1 plus 11 divided by 2. And that gives me the point 12, 6. Okay? 24 halves is 12, and 12 halves is 6. So now I can plot that point. 12, 6 is going to be right here. Now, without a doubt, we know that point is in the middle. And we can also eyeball it and look to see if they appear to be the same length. And they do. So I'm going to put my mark here, my mark there, and I'm going to label that point A. And now all I have to do is draw the little line segment that connects them, and I will have drawn this segment. Okay? Now, notice that we don't know actually what the distance from P to A is, and we can find that using the distance formula. But we do know for sure that A is the point 12, 6 by way of the midpoint formula, making segment RA the median. All right, another example. In triangle PQR, right here, we know that QS, this is QS, and RT are medians. So right away, I'm going to say if QS is a median, this segment is congruent to that segment. And if RT is a median, then I know that this segment is congruent to that segment. And I've got to put doubles there because they may not be congruent to these. Now, if PT is 3x minus 1, so this is 3x minus 1, and PS is 4x minus 2, and we know that SR is 2x plus 4, we need to find the length of segment TQ. We're trying to find that. Well, my gosh. I think if I knew what x was, I could plug it in here and find out what segment PT measures. And that would be what this is. But I can't find x by setting 3x minus 1 equal to the unknown. But notice down here I have two segments that are equal, and I have algebraic expressions that I can set equal to each other. So the first thing we're going to do is find x. So I will set this equal to this. Segment PS, the measure, has to equal the measure of segment SR. So 4x minus 2 has to equal 2x plus 4. Subtracting 2x from both sides, I get 2x. Adding 2 to both sides, I get 6. So I know x is equal to 3. Now I know that x is equal to 3, I can find out what the measure of segment PT is. It's going to be 3 times x, which I just found to be 3, minus 1. So that's going to be 9 minus 1, or 8. And since I know that PT, the measure of PT, is equal to the measure of TQ, well then TQ must also be 8. And that's the answer. Now if you have time, it'd be worth verifying that PS and SR, their measures are actually the same because I know what x is. So this would be 4 times x minus 2. That would be 12 minus 2, or 10. And if I plug it into the expression for segment SR, I get 2 times 3 plus 4, which is 6 plus 4, or 10. And that way we know we're doing the right work here. Another example. Segment AM and CN are medians of triangle ABC. So AM, this line here, segment, and CN, this line here, are both medians. And LX is a median of this smaller triangle, LMC. So this is also a median. Wow. We need to find the measure of XM. That's this here. If we know that BC, this entire segment, is 18. Well, let's see how we're going to do this one. We need a plan of action. Because AM is a median, I know that segment BM is equal to segment MC. That's this one here and the entire segment here, which I can't put a line on because then I wouldn't know which segment I was referring to. Well, since they have to be equal and the whole thing's equal to 18, I know each of those has to equal 9 because 9 plus 9 is 18. Well, now that I know that MC has to equal 9 and I know that LX is a median, then I know that the measure of segment MX has to equal the measure of segment XC. These two segments right here have to be the same. Well, XM is what I'm looking for. XM, remember, is the same as MX. Well, if they both have to equal total 9, then I know they both have to equal half of 9. So we can answer the question then. XM is equal to half of 9, or 4.5. Okay, so that would be the answer. So we're kind of working from big to small there. Another example. In triangle MOP, or MOP, we know that angle O, this one down here, is congruent to angle MPO, this entire angle here. That makes it an isosceles triangle. We also know the measure of angle M up here is 40 degrees. And then we know that PN is an altitude. PN is an altitude, which means that this angle is 90 degrees and this angle is 90 degrees. Now we're trying to find the measure of angle NPO. So here's N, here's P, here's O. We're trying to figure out what this angle measure is. Well, let's see if we can figure that out. If this angle up here, angle M, is 40, then I know that the measure of angle MPO, which has to equal the measure of angle O, they have to all add up to 180. Remember that? So this angle's measure plus that angle measure plus 40 have to be 180. That only leaves 180 minus 40, or 140 for each of these two. So if they both have to add up to 140, and they both are equal to each other, then they both have to equal 70 degrees. So 70 degrees equals 70 degrees. Well, now that I know that this angle down here is 70 degrees, and I know that this angle here is 90 degrees, now I can find what the angle measure of that one there is, which is what I'm looking for, because they all have to add up to 180. So I can say that the measure of angle NPO, which is what I'm looking for, this one here, plus 90 degrees plus 70 degrees has to equal 180. And if I subtract from both sides, minus 90 minus 70, I'll get the measure of angle NPO equals 20 degrees. So again, we have more than one setup per problem. These problems are now multiple steps. We have to basically gather our information, kind of go on a little hunt, see what we have and see what we need. Okay, we actually had to find what the measure of angle O was first in the big triangle, and then work with the little triangle to try and figure out what the angle that we were actually interested in was equal to. Okay? Now it's time for the point of the show that we call the Say What? Okay? And you know I've been referring in the beginning of the show to the concurrent points that were common for all the special segments. They all intersected at the exact same point inside the triangles. Well, they have special names. Okay? Let's look at the first one here. The first term for the intersection of these special segments is called the orthocenter. The orthocenter. And here's what the orthocenter is. It's basically the intersection of the three altitudes of the triangle. So if we look at this graph right here and zoom in on it, the altitudes, remember, were formed by dropping a perpendicular from the vertex. So this was 90 degrees, this was 90 degrees, and this was 90 degrees. And notice if we draw it, they all intersect at the point of concurrency, and that point of concurrency is called the orthocenter. Okay, moving right along here. The next nice name for a point of concurrency is called the centroid, and this one has a pretty nice application. The centroid is the intersection of the three medians. Okay, so let's look at this graph right here. The median, remember, is formed by dropping a line from the perpendicular, or from the vertex of one side to the opposite side, such that the two sides were congruent. Okay, so if I drop a line from this vertex, these two sides are congruent, and from this vertex, these two segments are congruent. They do intersect at a common point, a point of concurrency called the centroid. Now, here's the centroid. Here's what it means. The centroid would basically be the balancing point or the center of mass if this triangle had uniform density, if it was the same thickness throughout or had the same weight distribution throughout. You could actually find the centroid and balance a pen on the centroid, turn the geometric shape upside down, and you should be able to walk around the room with it balancing on your pencil. That's the neat application of the centroid. It's the balancing point. And it is the intersection or the point of concurrency for the three medians. Two more to go. The circumcenter. Circumcenter is basically the intersection of the perpendicular bisectors. Now, the circumcenter has an interesting name. It's very appropriate. Circum means to go around. Circumference is around the circle. So the circumcenter is going to basically be the center of a circle that we say circumscribes the triangle. So basically, it's a circle that will contain the triangle. So if I drew my three perpendicular bisectors, and I have my little compass here, I could put my compass point down at that circumcenter, and if I go out to any one of the vertices, it should measure the exact same distance. So I could then draw this line all the way around, and it would form that circle. So notice the distance from the circumcenter to each of the vertices is always going to be the exact same distance. Okay? And that's one of the nice properties of the circumcenter. The last special name for a point of concurrency is called the incenter. And the incenter is going to be the intersection of the bisectors of the angles, the angle bisectors. Now this also forms the center of a circle, but this is a circle that we say is inscribed inside the triangle. It's not circumscribing the triangle is actually containing it. So if I drew my three angle bisectors, that point of concurrency is the incenter, and it would form the radius then of a circle that would be contained inside the triangle. So the distance basically from that center, the perpendicular distance to each of the three sides, would be the same distance. So interesting names for some interesting points. Orthocenter, centroid, circumcenter, and incenter. Well, once again, I've covered quite a bit of information in a very, very short amount of time. So I hope you got it all, but remember that if you don't, or you didn't, and you have some questions over this episode or the previous episodes, you can email me at kcorpy@newbraunfels.txed.net, and I will get back to you as soon as I can. So until next time, I'm still Kevin Corpy, and I will still catch you on the flip side.
You're watching